This problem is about getting the phase margin from Bode plot. This problem is taken from ECE, GATE ECE 2014. There were 4 sets of questions. There is set 1. The phase margin in degrees for the system with a transfer function 10 by s plus 0.1, s plus 1, and s plus 4, calculated using the asymptotic Bode plot. That is, we need to get the Bode plot, phase margin simply from the asymptotic Bode plot of these transfer functions. Okay, so we are simply writing this transfer function and again splitting into this first order system. Of course, simply I have the same thing is rewritten. In first order form. First order form is like 1 by tau ps plus 1. So wherever possible, these numbers and all, you convert that to first order transfer function form. So this 0.1 will be going to the denominator here. So we'll be having, since we are dividing by 0.1, the denominator, numerator also do the same thing. Here it is now not a problem. And here again, s by 10 is there. So this 10 we have to bring it this side, otherwise we need to have this as 1. So in that way, divide this part with 1 by 10. So numerator and denominator. So done. Now we have this first order. Otherwise the given transfer function is written in terms of like a first order system in series. So we have again the multiplied content is having a kp of 10. Denominator we have these 3 contents. These are all nothing but the first order transfer functions of the form 1 by tau p s plus 1. And again ensure that before going to that, we need we know the thing what is called as a corner frequency. Corner frequency is nothing but always this tau omega equal to 1. Otherwise frequency corresponding to tau omega equal to 1. From that we'll be getting this frequency is omega equal to 1 by tau. Always this kind of calculation we'll be doing it for wherever we have this first order term, or not only with the first order transfer function, even with that PD controller also. Okay, we'll see that. What is the role of that? So tau d equal to 1 is a corner frequency. And from that we get omega equal to 1 by tau. So here we have tau equal to 10. So 1 by tau 10 is 0.1. And this for this is 1. And what we are doing actually, we are writing this transfer function in the order of increasing corner frequency. So this is having a corner frequency of 0.1, and next one is having a corner frequency of 1. This is having a corner frequency of 10. So that actually this Bode plot is having lines, simply straight lines, what is called as asymptotic lines in the limit of omega tending to 0 and omega tending to infinity. So these two asymptotic lines, assume this is kind of asymptotic lines for omega tending to 0 and omega tending to infinity. And these asymptotic lines are intersecting at the corner frequency. So first thing is getting the corner frequency so that we can locate the intersection point. With reference to that, we can construct the low frequency and high frequency asymptotic lines. So that's why we have first found the corner frequency. And here again, next thing is arranging the equation in the order of increasing corner frequency, because with increasing corner frequency, again with increasing frequency, a lot more data are going to be added till this 0.1. This will be having effect, and after then till that 1, this will be having more effect. And the thing is to arrange them in increasing order of corner frequency. Okay, that is done. Say for this 1 by 10s plus 1 corner frequency is simply, what is corner frequency? That is equal to 1 by tau. So tau is 10, so 1 by tau 0.1. So like that for the other one. So now we have this corner frequency of these first order systems in series. And here what we are doing this, though it is 0.1, for getting this phase plot, actually the phase plot is for the first order system, we know that the phase will be having the cross, what is called as in the phase plot, the curve will be actually having what is it, change of slope at the corner frequency. Raise, I will simply I will come to that. Say this for the corner for that frequency of 1.1, the phase angle is minus 45. For the first order system, the phase angle is ranging from 0 to minus 90. And minus 45, the exact midpoint is happening at the corner frequency. So here for this system, the corner frequency is 0.1. So at that corner frequency, the phase angle is minus 45. Of course, you can check that as well, how it will be. So this maybe one simple calculation we'll do that. So what is phase angle for your first order system, which is tan inverse of minus tau omega. Okay. And by always at corner frequency, tau omega equal to 1. So we have this is tan inverse of minus 1. Now tan inverse of minus 1 is actually having a phase angle of minus 45 degree. Of course, in the limit of omega tending to infinity, this tan inverse of infinity will be simply always tan inverse of infinity will get a phase angle of minus 90. That is a phase angle for the first order system ranges from 0 to minus 90 degree. 90 degree. The center point is at minus 45, which is happening at the corner frequency. So that's why. And again, additionally, the starting point, though it is starting at omega of 0, till the value of about 1/10 of the corner frequency, we'll see that the value is approximately 0. So raise, maybe I'll show that plot so that, say for example here, so this corresponds to, so assume this is your one such data. Here the corner frequency point is here, and till the 1/10 of this corner frequency, say here the corner frequency is 10, corresponding to that, the 1/10 of the frequency is say 1. Till the till the frequency of 1, the phase plot is phase angle is almost 0, and at the value 10 times of that, so at the value of 10 times, which means this frequency of 10, the multiplier 10 is 100. This phase angle plot is nice straight line. Obviously, you can. This is also what is called as a asymptotic phase angle plot. But normally these asymptotic lines we'll do for this gain plot. Even for the phase plot also we can do, at least for systems like first order and PD controller, PI controller, like that. For second order system, because of this effect of this zeta, it is slightly tricky. Okay, but now we'll see that maybe with the example in the coming class. Okay, now what did we do? These corner frequency points are 0.1, 1, and 10. So for the 0.1, 1, and 10, in addition, we also have the other data, 1/10 of this 0.1 and 10 times of this 10. So that this is to get the phase angle till a point of 0.01. For the corner frequency of 0.1, the frequency is roughly about 0. And at the point 10 times of this, the phase angle is roughly minus 90. So in that way only, actually this line is plotted. Actually, I have this overlapping blue color line, which is the overall plot. I will assume this line is extending here. So here the corner frequency is 0.1, and 1/10 of is starting here, and 10 times is here. So this is simply a nice straight line, which is approximate line. Otherwise, it will be like kind of going like this. Otherwise, it will be like going like, okay. Some deviations in these endpoints. Otherwise, it is most of the parts are matching in this line. Okay, that's why we are finding this 1/10 and 10 times of that. Okay, now coming to the next thing. This is corner frequency is simply 1. For at 1, the phase angle is minus 45, and 1/10 of 1, which is 0, and 10 we have at minus 90. As like that for 1 by 0.1, yes, here the corner frequency is 1 by 0.1, which is 10. So at corner frequency, phase angle is minus 45. Okay, now we have this phase angle for everything thing, every first order system. Now the total phase angle is simply the summation of these phase angles. Or is in the range of at the frequency of 0.01. What is the phase angle? Add every value simply 0 here. At the value of 0.1, which is minus 45. No, that other things are simply 0. At 1, we have minus 90, minus 45. Add them to get minus 135. At value of 10, we have minus 90, minus 90. So we have this. So this way you can get this what is it, the corner frequency, what is it, the phase angle for every range of so at every point of omega is available. At least there are 1, 2, 3, 4, 5 points available. We can make use of them and we can plot them. Say at 0.01 we had a value of 0, and at 0.1 we had a value of 45, and 1 we have this value of 135. So, and before that, so these lines, this first line corresponds to the first system, which is 1 by 10s plus 1. 1 by 10s plus 1 is having this phase plot, or simply 1 by 10, this 0.1. At this point, it has to make a straight line of slope 1. So this green line is for 1 by 10s plus 1, and the next darker green line is for 1 by s plus 1. So this for 1, the phase angle is minus 45, simply straight line. Okay, and for the next one, which is 1 by 0.1 s plus 1, so there is corner frequency is 10. So we have till that 0.1, this is, so till 1 the phase angle is nearly 0. After then this having this line. Okay, now the overall plot, this blue line curve, is simply obtained by adding the phase angles, check for every frequency. So 0.01, 0, 0.1, this is 0, and this is 45. So total is 45. And for 1, we have this is 0, this is 45, minus 45, minus 90, minus 135. So minus 135 line is here, point is here. And for this 10, we have this is minus 45, 135. Yeah, that's right. Yeah, this is, sorry. Fine, wait. And yeah, this is minus 45. This is minus 90, and there is one more minus 90. This darker green and light green. All are having minus 90, minus 90. So 280, 180, and 45, 225, that point. So simply this phase plot also you can simply draw that using the slope. Of course, the this axis is in linear. Here we have the log scale for frequency. So always we have constructed the phase plot from the given data of for the given system. And what is the objective again? Let's not forget. So we need to get the phase margin. So for phase margin, what is mean by phase margin? For that, the phase margin, we'll come to that. Yeah, before phase margin, let us also plot this gain plot. Gain plot is what are all there. So we have a gain term and first order terms. Okay. So for the gain term 10, we can simply plot this nice horizontal line, which is having a slope of 0. This red line corresponds to the gain plot, or also called as amplitude ratio plot for this 10. Okay, next thing is next thing is simply this 1 by 10s plus 1, 1 by s plus 1, 1 by 0.1 s plus 1. So 1 by 10s plus 1. So that is the gain plot will be simply at the corner frequency we'll be having the intersection of this low frequency and high frequency asymptotes. So the corner frequency for 1 by 10s plus 1 is simply 0.1, or is this tau equal to, sorry, omega equal to 1 by tau. Tau is 10. So 1 by 10, that is 0.1. So this is a point. To the left, we put this horizontal line of 0 slope, or is horizontal line. And from that point, you put a line of slope minus 1. So minus 1, this is correspond, or is this rectangles of unit size. And again, in plotting, always ensure that you have the same. Of course, we'll be having the same scale, no? 0.1, it will be 1, it will be 10. So these are all fine. So the same thing, there is gain and frequency are having the same intervals, no? Same intervals. Okay, now this -1 and this is having a slope of 0. Next thing is for the another first order system in series, which is 1 by 10s plus 1 till a value of 1, the low frequency value is simply 0, and beyond the value of 1 we have slope of -1, and like that for the next thing 1 by 0.1 s plus 1. So that's why we have actually arranged this in the order of increasing corner frequency till a point of always at a point of point till a point of 0.1 we have this line, then after then another horizontal so another thing, and another thing. Okay, now what is needed is to get the overall gain plot. So for that simply start from the highest thing. We have the gain is 10, and now this point, no, till the lines are horizontal, no worries, and after that there is a negative slope. So always we have to make one more table, so that always we need to account for the slopes of this AR or slope of these lines or gain plot. So for that we'll make one more table, what is called as this table till a value of 0.1. So till a value of 0.1, this is going to have a slope of 0. In that way, we are writing for the range of frequencies are 0 to 0.1 and 0.1 to 1, 1 to 10, and 10 and beyond. So because at a value of 1, we have another kind of frequency is there. At another value of 10, also we have a kind of frequency. After that, we have no other thing. So for 10, of course, it is a horizontal line. The slope is simply 0. And for 1 by 10s plus 1, this corner frequency is 1 by 10. So at a value of till a value of 0.1, the slope is 0. And from this 0.1 onwards, or is maybe I can also put this 0.1 onwards, we have negative slope and till a value of 1. Till a value of 1, till a value of till a value of 1, we have this. After that, this another line is also getting up. So there is this correspond is a amplitude plot corresponding to 1 by 10s plus 1. So that is also now getting a slope of -1. That's why we have this another line, another kind of thing coming up, which is having a slope of 1 minute. Yeah, right. I'm simply writing for the 1 by 10s plus 1 for till the range of uh, till the range of 0.1 we have slope of 0, and beyond that it is slope is -1. It is simply like from 0.1 to till infinity slope is -1. And for this 1 by 10s plus 1 by s plus 1 till a value of 1 the slope is 0. After that slope is -1. Fine. And after that like that, this is for that value till 10 slope is 0. After that -1. Now for every range you can simply add the slopes. So we have for this range of omega, slope is totally 0, and here in this range slope is simply add this. This is we have -1, and for this we have -1, -1, -2. So now these things are to be plotted till a omega of 0.1. We have slope of 0 till a value of 0.1. We have a value of 0. Yeah, we have to use this, no? Till a value of 0, it is so till a value of 0.1 slope is 0. Of course, we are starting with the highest gain value. Already this line is corresponding to k of 10. So till that thing the slope is 0, and from that to or is 0.1 to 1. From 0.1 to 1. From 0.1 to 1 we have a slope of -1. Of course, that line is having the same slope for rest of the thing. Or is before going to that, we can construct the Bode or is these asymptotic lines for everything, every system. The total is simply till the point of 0.1, there is no change of slope. Entire thing is having the thing. So we have this till a value of 0.1. We have this blue line represents the total. So this is having slope of 0. And from then, here we have the slope of -1. So from then we have to start another line. This is drawn so as to have a slope of -1. So -1 is simply there is negative slope. And from otherwise you have to use the last line information. And from that, from 1 to 10, the slope is -2. So 1 to 10, from 1 to this is 1 and this is 10. From 1 to 10, the slope is -2. So -2 means in the y-axis 2, x-axis 1. So simply draw this. There is a here it is change of slope. Again, there is another change of slope. You can also easily understand that because this is -1, this is -1, whereas this is 0. So that's why this is having -2 slope. And that point onwards, now we have 1, 2, 3. 3 lines of -1 slope. So totally -3 slope. So -3 slope is, we already written that, no? Or simply we are going to plot this, make the lines representing these slopes. Of course, the starting point is always from the highest amplitude line. The highest amplitude line is here, 10. From the point of 0.1, we need to make again a straight line of slope -1, again straight line with -2, and from this point it is straight line of -3. That and all you can easily understand from the available plots. So here we have slope of 0. Here in this region slope of -1. In this region we have slope of -2, and here we have slope of -3. Of course, for all the further it will be going. Okay, now what is needed is phase margin. So what is the meaning of phase margin? That is to be understood. And phase margin is nothing but the value of the amplitude phase angle corresponding to a amplitude ratio of 1. Say for example, where is amplitude ratio of the overall line? So this is amplitude ratio. This is amplitude ratio line, this blue color line. And phase margin corresponds to the phase angle, or is a I will again repeat again. So let us see. So see, we have this is the amplitude ratio of the overall Bode plot. At this point, the amplitude ratio is 1. Okay, corresponding to that, you simply make a vertical line and go up to the overall phase plot. So what is the angle? So this is a phase angle corresponding to the amplitude ratio of 1. So phase angle, this is the 135 we are getting from the phase angle of phase angle corresponding to the amplitude ratio of 1. That has to be, of course, that is -135. And phase margin is actually 180 minus of the phase angle corresponding to, or is the phase margin is simply the 180 degree minus the phase angle corresponding to a amplitude ratio of 1. So the phase angle corresponding to a amplitude ratio of 1 is equal to -135. Service, this is 180. Simply again, this is actually phase lag. Is 180 minus phase lag corresponding to the amplitude ratio of 1. So the phase lag is 135. Fine. So is 180 degree minus 135 degree. So this 45 degree is the additional angle available over and above this 180. There is how much gap available between this point and 180. So that is the phase margin. And additionally, we can also find gain margin. Actually, that is not asked, but still we'll see also what is gain margin. So gain margin corresponds to the corresponding to a phase angle of -180. Simply go up to the amplitude ratio plot and get the value of this AR. That is actually here it is M. So that value is taken as M. So your gain margin is actually equal to 1 by M. So this is your 1 and this is M. So 1 by M. This gap is actually coming as gain margin. So gain margin for a stable control system, gain margin should be greater than 1, and phase margin should be a positive content. It should be It should not be equal to 0. For a stable system, phase margin should be greater than 0 and gain margin should be greater than 1. So these are all the guidelines actually from Bode plot stability. We are not asked to do that. Still, what is asked is the phase margin of this systems in series. Okay, I will repeat this entire thing again. Here, we need to get the phase margin of this system. For that, we are writing this thing in terms of nicely rearranging to first order systems in series with increasing corner frequency. What is corner frequency? Tau omega equal to 1. So we know this tau is 10. So what is the omega? Omega equal to 1 by tau. So these are all written. So these things are having this increasing corner frequency 0.1, 1 and 10. As I said, this for first order system at a value of tau omega minus tau omega, phase angle is minus 45. The phase angle ranges from 0 to 90 for the first order system. So of course everything is a first order system. And for 0.1, 1 and 10 we need values. Additionally, we also write this data for 0.01 and 100. This is 1/10 of this corner frequency. This is 10 times of the corner frequency, like that. So now we have for the midpoint, the values are written. Okay, like that. For the next highest point, say we have this for 1, the highest, these values are simply 90 forever. These are all 90. So these are always, and after writing that, simply get the total phase angle for every corner frequency. Simply get that, simply add them, nothing great. Simply add them, you'll be getting this. So using this, you can construct the this phase angle plot, which is needing the data of omega, which is simply omega and phi. So you'll be having this plot. Now, this is about amplitude ratio plot or gain plot. So for that, again, here now we need the slopes. For getting the slope, we are using this low frequency and high frequency asymptotes. At the corner frequency, the asymptotes are meeting. So first thing is arranging this in the order of increasing corner frequency. That already we have also done for that. And till a frequency of 0.1, the slope of this is simply 0. After 0.1, slope is -1. Like that, till a frequency of 1, this is having 0 and -1. So okay, that way you have written the slope for everything. Then get the total slope, simply adding them. Okay, and in constructing this this gain plot, of course, this is for the thing for the first system, and next thing is for the second system, and this is for the third system. All are in series, and already there is a gain of 10. So starting from the highest gain and make this overall line till a point of 0.1, we have the slope of 0. After that, slopes are different. So for that range, you make these lines. So these lines you can easily do because these are all having is 1 and 1 units. So by that way, we have this total amplitude ratio, and earlier we also had this phase angle plot. Now, getting this phase margin. To get the phase margin, what is needed is starting from the gain plot at a value of AR equal to 1, nicely draw a vertical line so as to get so as to meet at the overall phase plot. So what is the value of this phase angle? Phase angle corresponding to a this phase angle corresponding to a amplitude ratio of 1 is noted, and the phase margin is 180 minus of this phase lag. 180 minus of the phase lag corresponding to AR of 1. Okay, that is, so here we have a phase margin of 45 degree. Okay, and gain margin is for getting the gain margin, we are starting from the bottom here, corresponding to a phase angle of minus 180. From that point, you go up in and meet the gain plot, and what is the value of this amplitude ratio, that you take it as m, and the gain margin is equal to actually 1 by m. So 1 by m will be 1 by 0.1, that is equal to 10. So this problem is having a phase margin of 45 degree, which is greater than 0, and gain margin of 10, which is again greater than 1. So the system is also, you can say, like stable from the perspective of Bode stability criteria. Okay, again, what is the angle here? The phase margin is simply 45 degree. There is an answer to be written. So this carries a weightage of 2 mark. But additionally, we also discussed about making this Bode plot and the related additional aspect what is called as gain margin also.